Have you ever stopped to think about how one single tiny particle can exist as a solid, a liquid, and a gas? Today, we're going to follow the amazing life of one of these molecules to really understand the world around us. Let's dive in.
I mean, it sounds kind of wild when you say it out loud, right? A hard, solid block of ice, the liquid water you drink, and the invisible steam that comes from a kettle, they're all made of the exact same stuff. So how on earth is that possible? Well, let's find out.
The whole secret comes down to these tiny little things. Molecules. For our purposes, they are the absolute main characters of our story today. Everything that we're about to see is all about how these molecules act, how they hang out with each other, and, how much energy they have to dance around.
All right, so first things first, what even is matter? It sounds like a super scientific, complicated word, but I promise you it's not.
Seriously, just look around you right now. The chair you're sitting in, the air you're breathing, your phone, it's all matter. And all of it, every last bit, is just a giant collection of these molecules that are always, and I mean always, moving, vibrating, and bumping into each other. The way they're arranged and how fast they're moving, well, that's the whole secret.
Let's think about the three main states of matter, solid, liquid, and gas, as different kinds of neighborhoods that our molecules can live in. Each neighborhood has its own set of rules, its own little vibe.
Here's a quick little cheat sheet for you. You can see right away, solids are super rigid. They've got a fixed shape and volume. Gases, on the other hand, are totally wild. They don't have a fixed shape or volume. And then there are liquids, right there in that sweet spot in the middle, able to flow wherever they want but still keeping the same volume.
Let's make this even easier. Picture a solid. Its molecules are like people in a movie theater with assigned seats. They're packed in there super tight. They can fidget in their seats, vibrate a little, but they can't just get up and swap places. Now, a liquid is totally different. That's more like a busy school hallway between classes. Everyone's still packed pretty close together, but they can slide and weave past each other, which lets the whole crowd flow and change shape.
So if a liquid is that crowded hallway, a gas is like a huge game of tag in a giant open park. The molecules have so much energy that they've completely broken away from each other. They're just zipping around super far apart, and they'll expand to fill every single nook and cranny of whatever you put them in. Okay, so how does a molecule pack its bags and move from one of these neighborhoods to another? Well, the secret ingredient, the real key here, is energy. And usually, we're talking about heat. That's what gives them the power to make a great escape. It's actually a really simple chain reaction. First, you add heat, which is just energy. That energy gets the molecules all excited, and they start to vibrate and move way faster. As they speed up, the forces that hold them together get weaker and weaker until they finally just break. And boom, just like that, you've got a state change.
So our first great escape is called melting. Let's go back to that ice cube. As you add heat, its little water molecules start to shake so violently that they literally break free from their assigned seats. They don't have enough energy to fly away just yet, but now they can get up and start sliding past each other. But what happens if we keep cranking up the heat? Well, that's when we get to the next level of freedom, vaporization. The molecules in the liquid start moving faster and faster until, eventually, they've got so much energy they can completely overcome the forces holding them back and just leap out of the liquid into the air as a gas. We call that steam.
And here's a perfect real-world example: sweat. Ever wonder why it cools you down? Well, that liquid on your skin is absorbing your body heat. That heat gives the water molecules enough energy to vaporize and fly away. And when they leave, they take that heat with them, which makes you feel cooler. It's basically your body's own personal air conditioner. Pretty cool, right? But hey, this isn't a one-way trip. What goes up must come down. We know adding heat gives molecules the energy to escape. So what do you think happens when those super energetic gas molecules start to lose their energy and cool down? This is called condensation. As those gas molecules cool off, they slow way, way down. They can't fight off their natural attraction to each other anymore, so they start to clump back together into a liquid. You've seen this a million times. You lift the lid off a steaming pot of pasta, and the inside of the lid is covered in water droplets? Yep, that's condensation in action. And if we keep removing heat, we reach the final step of the journey home: freezing. The molecules in the liquid get slower and slower until they just don't have enough energy to move around anymore. The attractions take over completely, and they all snap back into that rigid, fixed pattern. The busy hallway empties out, and everyone's back in their assigned seats.
Now for water, these temperature points are probably super familiar. We all know that below 0 degrees Celsius, it's solid ice. Between 0 and 100 degrees, it's our everyday liquid water. And crank it up above 100 degrees, and you get gaseous steam. It's a perfect little summary of the journey we've been on. Okay, now for the really, really cool part, the exceptions to the rule. What if our molecule could take a secret passage? What if it could just skip a state entirely? Well, under just the right conditions, it absolutely can.
That's right. Sometimes matter just decides to skip the middleman.
This first amazing shortcut is called sublimation. The most famous example, which you've probably seen, is dry ice. That's just solid carbon dioxide. You'll notice it never melts into a puddle of liquid. Nope, it goes straight from a solid block into that awesome, spooky-looking gas. And, of course, the reverse trip can happen too. It's called deposition. This is when a gas gets really cold really fast and turns directly into a solid, completely skipping that liquid phase. You know when you wake up on a frigid morning and see those beautiful, intricate ice crystals on the window? That's deposition. It's just water vapor from the air turning directly into solid ice.
So with all these different paths and secret shortcuts, things can get a little confusing. How do we keep track of it all? Well, luckily for us, scientists created what is basically the official roadmap for any molecule's journey.
This is a phase diagram, and it's awesome. It's a map that shows you exactly which state a substance will be in at any given temperature and pressure. The lines are the border crossings where phase changes happen. And see that spot where all the lines meet? That's the famous triple point, a very specific, almost magical condition where a substance can be a solid, a liquid, and a gas all at the same time, in perfect balance. How wild is that? But this map brings up one last little mystery. If you were to graph the temperature of an ice cube as you heat it, you'd notice something really weird. While it's in the process of melting, the temperature just flatlines. It gets stuck at 0 degrees Celsius, even though you keep adding heat. So what's going on? Why doesn't the temperature go up?
And here's the big reveal. All that energy you're adding isn't making the molecules move any faster, which is what temperature actually measures. Instead, that energy has a different job to do. It's being used exclusively to break the bonds holding the molecules together as a solid. The energy is 100% focused on the task of changing the state. As soon as all the ice has melted, then the temperature can start to climb again.
So here's the key takeaway. Energy can either raise the temperature or it can change the state. But during that change, it can't do both at the same time. And this whole map, this incredible journey, it's different for every single substance out there. Carbon dioxide, nitrogen, even iron, they all have their own unique phase diagrams. So now that you know how to read the math, what other incredible molecular journeys are out there just waiting to be explored? Ever wonder what the phase diagram for a diamond looks like?